Hi there, this is Mark Fawcett, and with me is Ernesto Amaral and Luz Cisneros and Peggy Karras. And together we're doing an experiment this summer with the blessing of Pat Goldsmith, our interim department head, who has given us some support to help do this. So the experiment is to have informal workshops or information sessions where we discuss methodologies that people may want to consider using in their thesis and dissertation projects, in course papers, and just general research. And we sometimes will cover topics that previously have been covered in the required course sequence and methods in the department. But mostly, and especially pointing toward the future, we will try to do short workshops or sessions focusing on methods that probably were not covered in the required coursework. The intention is not that at the end of 60 minutes you would be an expert in the new methodology, but rather you would have some appreciation for why it exists, how it might be implemented in an empirical analysis, with some reflection on pros and cons for choosing this method as a way to address a research question. And then if there is further interest, we could potentially have a second session on that, or people could be directed toward other opportunities to learn more about it. And in the summer, this summer, 2021, Ernesto and I are going to cover 6 topics. There was an informal survey, not quite really a scientific representative sample, but we got some ideas through an informal survey of some topics that might be of interest to people and that we could cover on relatively short notice. So we have those topics identified, and we'll do 6 sessions over the next couple of weeks. And if people find them useful, we're going to record that feedback and then try to replicate the same approach in the regular academic semester and also in the summer of 2022. If we were pointing toward the future, if people find these workshops, these sessions useful, we will try to bring in other people, faculty in the department, or maybe faculty from outside of the sociology department, who in their own work use particular methods that we think might be interesting to at least a subset of the students in sociology, and have them give kind of a hands-on overview of the methodology and the benefits that come that the method brings, and some awareness of the limitations and maybe, peculiar characteristics that you have to watch out for, and so forth. So we could go in a lot of different directions in the future. We appreciate everybody who's joining, making the time on a voluntary basis here in the summer. This is not for credit. It's strictly because we're all curious people and interested in learning new things and maybe applying them in our own work. A sub-theme for this summer experiment is to, help emulate or to some of the culture that we've seen in other areas in the department here at Texas A&M and in departments that we have connections to in the past. And the culture that I'm referring to is the culture of informal working groups that seek out information, knowledge about practices at the bleeding edge of either theory, methods, or other research practices, not because it's for course credit, but because we're interested in learning as much as we can while we have this opportunity. And in my own experience as a graduate student, I learned as much or more in settings like that as I did in formal classrooms. And that's not a knock on the formal courses that I took. It's an appreciation of the exciting culture that existed in the graduate department that I was taking courses in. And we have some of that going on here in the department at Texas A&M. There's a social psychology group that meets regularly. The race and ethnic relations group has workshops that meet. And so this is a workshop that will meet to review methods. So I've got a reputation for being long-winded. It's well justified. So I have to self-monitor and bring my remarks to a halt before they get overly long. Ernesto's graciously agreed to start off with the first couple of sessions here. Again, welcome everybody. Please let us know what you think, how things could be improved, and especially imagine what this could be in the future if we had more time to prepare and think through. And, we hope you have a lot of questions and that those questions will prompt refinements and additional sessions beyond what we're doing this summer. So with that, thanks to Luz and Peggy for their assistance here with getting things organized, and to Ernesto for agreeing to be first up. And I'll silence myself, and Ernesto, take it away.
Hey, thank you, Mark. So thank you very much, and also like to thank Luz and Peggy for helping us, and thank everybody to be here. It's a great attendance, and so it's awesome. I will share my screen here now, and I will throughout my let's say like this lecture, just you can feel free to unmute yourself and just ask the question. If you want to ask in the chat, I might not be able to see it, but then if you do, then Peggy or Luz can just read the question to me, because some of these questions, they're better to be asked throughout the presentation instead of at the end. So let me just share my screen here and just start showing you the, I don't see anybody now. This is the website that we're going to be posting the materials for this talk, and the link is the one that I just put it there on the chat. And I don't know, for some reason I don't see any one of the videos here. I don't know. So here we pretty much have the program, and the program lists the 6 topics that we're gonna cover this month. And in the website here as well, we are, like the way that we are doing, both Mark and I, we are uploading our files into this Google Drive folder that everybody can have access just by clicking here. And after we organize the folders there, we will also upload the files within each one of these the lectures here. So far, we just have the lecture for today and this compressed file with some data file and this data, and also this website that some of you might know. That's a course that I taught at the spring 2020, and it was an introduction to social statistics using this data. And pretty much those people that attended that workshop, they realized that the first lecture that I will talk today about sample weights is all based on this one here. And the lecture on Thursday about OLS regression is all based on this one here. I did add some slides into this lecture, but it's basically the same thing. And then the same thing for the lecture on Thursday. I would just stop sharing here. I don't know why I cannot. I have to remove the spotlight or something. So I don't see anybody. Yeah, I don't. Oh, there's a hidden on the screen. Good. It's good to see some faces, what I thought. So I will start with this this lecture on analysis using survey weights. It's something that usually is considered to be really technical, but it's important for us to understand it because most of the surveys that we use, we have to include survey weights into the analysis. So let me just start here. And so the way that I organized the lecture today is to first explain what is inferential statistics, why do we have weights, and since we have specific samples of the population, it's good for us to analyze those samples and trying to do the analysis for the whole population. So the weights are important for us. And this is, I will just briefly talk about inferential statistics here. And then try to explain in a really straightforward, non-mathematical way, what are sample weights. And then I will give you some examples of how are the different options of weight that we can use in Stata. And then afterwards say that some surveys, some surveys, they have a complex sample cluster design. And if we do have that case of a complex design for specific surveys, we have to take that into consideration as well, mostly when we are estimating standard errors of statistical significance and so on. And I will give you some examples of how to use weights in the American Community Survey and also give you just the commands that we would apply using the General Social Survey. So these are two major surveys that sociologists use here in the country, and I will focus on these two here on this presentation. And then I will give you some examples of descriptive statistics, taking into account weights, and also taking into account the complex sample cluster design. So usually social scientists need inferential statistics. I mean, almost we never collect data from the whole population. We don't implement a questionnaire to the whole population of interest because of limited resources, not enough time, not enough money. So we have to select a subgroup of that population in order to analyze the whole population. So what we pretty much are trying to do is to use samples, a subgroup of our population, to make generalizations about that population, right? So just to be clear here, population is the total collection of all cases in which the researcher is interested. If I have a specific population and I collect information from all of them, I have a census, right? The census would be just pretty much the collection of information from all people in that population, implement the questionnaire on everybody. And samples are carefully chosen subsets of the population. Why carefully chosen subsets of the population? Because I want to have in my sample all subgroups of my population represented in a way that the estimates from the sample, the means, the median, proportions for specific subgroups, they can be generalized to the population. So whenever we are collecting, implementing the questionnaire for a subgroup of the population, for a sample of that population, we have to be careful with that. And of course, whenever we do samples and trying to be representative and make generalizations to populations, it's always good to work together with a statistician and some other people that have more knowledge about how to do a correct sample design in a way that you collect information for a subgroup that represents the whole population. And after, if we have the implementation of appropriate sample design, what happens is that those, the data that we finally have, the database is gonna have some variables to tell us how much each one of the individuals are worth in order to generalize about for the population as a whole. So we pretty much have to use specific techniques to make these generalizations. We get the sample, use the weights, and then we can make generalizations about the population. So we are pretty much trying to use a sample to understand a population. And just to be clear again, if I get indicators from this group of people that answer my questionnaire here, so if I analyze the characteristics of people from my sample, I have a series of statistics. And if I had a census in which I collect information about the whole population, and I generate indicators here, I would have the characteristics of my population that they would generate the parameters. So statistics are the characteristics generated from the samples, and parameters are characteristics originated from the population. Since I don't have a census, what I usually do is to use these statistics from samples and trying to generalize them to the whole population, trying to find the true parameter of the population. So here, this is one table that I try to explain the logic of weights. And this table here was one day that I was in a bar with a friend in Brazil, and he was asking me about weights. And then I just start drawing in the napkin, and I was like, oh, this is cool to explain weights. And then I put it in a PowerPoint and I started using since then. So let's say that we have a population of 10 people, specific population of interest of 10 people. But it's too expensive for me to implement questionnaires for all these 10 people. I will just collect information from 2 people. And in this case, I will implement questionnaire to José and another one to Maria. So I pretty much just have a sample size equals to 2. 2 individuals answer my sample, one is José and another one is Maria. But based on previous information, usually from census, from larger surveys, for example, from the Census Bureau, I actually know that overall in this population of 10 people, I have 4 men and 6 women. So I calculate these weights here for José and for Maria. So the answer from José will count it for 4 people, for the 4 men that are in that population. And the answer from Maria will count for the 6 women in that population. How do we calculate this specifically? It's really based on previous census, on larger samples that were estimated for that specific population. And I knew that I had 40% of men and 60% of women. But here, I'm not just collecting information about their sex, I'm collecting information about a series of other variables that I might have interest on. Opinions about politics, income, occupation, age, and so on, race, ethnicity, and so on. So I'm expanding the weight here in this example just based on their sex. But I can collect in my sample, in these 2 questionnaires here, a series of other characteristics of these people. And what the weight is going to do is, like, all answers that José gives, I'm going to pretty much apply them for all men in that population. So in my database, what I'm going to have is going to be a variable for weight in which it's going to have the value of 4 for José and 6 for Maria. So if I want to generate a table, instead of doing a table without the weight, that would give me 50% of men and 50% of women, I have to inform the weight. So I'm going to have 40% of men and 60% of women, and more in this specific way. I'm going to say that I have a total population of 10 individuals. I'm expanding to the population size. But sometimes I don't want to expand my sample to the population size. I want to maintain this sample size here of 2, but I want to take into account these different weights. So how I do this, I pretty much, that's in this case, you multiply 4 by 2 divided by 10, 0.8, 6 by 2 divided by 10, 1.2. This is what Brazilians call like a rule of 3. I have here 1, 2, 3 numbers, trying to find this one, 1, 2, 3 numbers, trying to find this one, which is pretty much this formula here that is at the bottom of this table. So in this case, I am still considering that I have 60% of women and 40% of men, but I'm maintaining the sample size. And I'm going to explain in which cases it's better to do this instead of trying to expand the population size. When we do weights for just do a table, simple table, descriptive table, and we want to estimate the absolute number of people, if we want to expand to that 10 people in my overall population, and I want to know that information for a specific area or for a specific subgroup, which subgroup? Maybe a subgroup by age, by sex, by race, ethnicity, and so on. We use weights to expand to the population size. However, if we use a sample to estimate the proportion of people in a specific subgroup, and I'm not really concerned about expanding to 10, but I just want to know the proportion here, 40 and 60%, and so we are not concerned with the absolute value, we use weights to maintain the sample size, and we focus the interpretation on percentages. And actually, for example, the American Community Survey, ACS, we can do both of these things here. We can use weights to estimate the absolute number of people in the US population, or also just focus on percentages. The way that the weights are constructed in the general social survey, we can just do this way here, right? So that's something that I'm going to show. I'm going to talk about when I focus on the general social survey, GSS. When I have regressions, which kind of weights should I use? And here, this formula, I don't want you to memorize anything. I'm just doing all this here. And this is an example in which I have a linear regression with one independent variable only, explaining my dependent variable. And when I have a simple linear regression, one independent variable explaining my dependent variable, the test of statistical significance for a specific coefficient beta, the Ttest, is estimated this way here. We get the coefficient that was estimated in the regression for that specific variable and divide it by the standard error of that coefficient. What is the standard error? It's kind of like a standard deviation of my coefficient. My coefficient is a point estimate is one number, but we know that it can vary a little bit to a higher or lower value. So we can have a confidence interval of this coefficient here. And the standard error of this coefficient is going to give me that. How do I calculate that? So the standard error is the square root of the mean square error, MSE, divided by the total sum of squares for x. And I'm just breaking it down little by little. The mean square error is pretty much the residual sum of squares, how much the observed values that I have in my database are distant from my predicted values from that regression. So it's pretty much the error term here. divided by the degrees of freedom. So that's the MSE. Degrees of freedom in the case of a simple linear regression, it's n minus 2 because we are estimating two statistics, the slope, beta 0, and the intercept, beta 1 from my independent variable. So that's why these degrees of freedom here is going to become n minus 1, and the residual sum of squares, I'm just using this here. And the corrected sum of squares is how much each one of the individuals related to my independent variable vary or distant from the mean for that specific variable. From all this here, why I'm talking about the Ttest to talk about weights for regressions. I want to focus on this little guy here, the sample size. This is the sample size of my specific survey that I collected. I calculated the coefficient, that's the association between my independent variable and my dependent variable, between my x and my y. And I want to focus here. Let's just, if I use a weight that expands to the population size on regressions, what would it happen? So let's say that instead of using the weight that maintains the sample size in 2 in my previous example of Jose and Maria, I expand that population size into 10. So I would, if I did that, I would be incorrectly informing the statistical software that I actually collected 10 questionnaires, not only 2. I would be telling the statistical software that I have a sample size of 10. So this would artificially increase the test of statistical significance for the coefficient. Why? Because my n here, my sample size, would increase from 2 to 10. This example doesn't seem that big, but I'm increasing it by 5 times, from 2 to 10. If I increase this denominator of the whole denominator will decrease in size. This whole denominator decreasing in size, everything here will tend to increase. So instead of telling the statistical software that I collected 10 interviews, 10 questionnaires from my population, because I didn't, I just collected 2, I have to inform the weight related to the sample design, but we should maintain the sample size. So we should still have 2 here and not 10. And just to show you, I'm trying to just show some basic things that you guys saw in previous statistics classes that you attended, and just showing this Ttest here in the distribution, the curve of the T distribution. And again, it's an example for degrees of freedom equals to 2. So if in that case, I told the statistical software that instead of 2 people, I had 10, my estimated T would tend to be bigger, and would tend to go to the right here or too much to the left if my beta was negative, my coefficient. But if it was in magnitude, it would increase, and let's say that we're talking about a positive value, would be to the right. By doing this, having a bigger Ttest, it gives a bigger Ttest gives stronger statistical significance. And by having a stronger statistical significance, we're going to have a smaller p-value. So we're going to have a smaller will be the probability of not rejecting the null hypothesis. So in some cases, my coefficient here might not be so strong, but because I have such a large sample size, I will get statistical significance. So that happens a lot with the American Community Survey, for example. Even in some coefficients that are really, really close to zero, I still get statistical significance because the sample size of the American Community Survey is so large, right? But I have to be careful about maintaining the sample size. And if I do that, I will be telling the statistical software the correct way to estimate the statistical significance. Otherwise, I will tend to have a really small p-value, and I will tend to accept the research hypothesis, which is the one that goes in the it's contrary to the null hypothesis. And this is just a summary of how we usually reject a null hypothesis or accept the alternative hypothesis, our research hypothesis. So the smaller the p, we tend to reject the null hypothesis compared to the significance level, and the larger the p in comparison to the significance level, we tend to accept the alternative hypothesis. And the significance level is pretty much related to the confidence level, our success rate that we are doing an estimate that's representative to the whole population, right? So this is, the p-value is the probability of not rejecting the null hypothesis. So this all just to tell you that for regressions, we have to maintain the sample size. So here I have an example of microdata. This is actually an extract from the 2018 ACS. And we have this strata variable, this cluster variable that I'm going to talk about it later. And here we have the variable for weight. This individual here is one person. It's going to count for 56 people. This person here is going to count for 143 people. So the answer from this person is going to count as that person is given that information for 143 people in total. And the American Community Survey also gives the household weight. So this person here in this household is representing a total of 56 households. And we're going to have a series of characteristics of those individuals. Here, I'm just showing sex, age, and income, but I have a series of other variables that is collected in the 2018 ACS. So how exactly we use these weights here in Stata, and how exactly I expand to the population size or I maintain the sample size. There are several options within Stata for weights. First one is the F weight. It expands the survey size to the population size. It indicates the number of duplicated observations. It used on tables to generate frequencies, but it can be used in frequency distributions only when the weight varies discrete. There are no fractional numbers. So it does work in our case because we don't have decimal cases here in ACS, okay? So we pretty much just do a symbol. This is a frequency table of X, of a variable X. And then in between brackets, I inform F weight equals the name of the variable weight. In our case here, it's going to be this PERWT is going to be my weight variable. And the X, if I want to do a table by sex, I substitute X by sex or by age or by income. In this case, is continuous, so it will not be a table. Okay. Let's say that we have a weight in my specific database that has fractional numbers. Stata is not going to work with you with F weight, so you have to use the I weight. The I weight actually, if we wanted, we could produce our own computation within Stata to adapt the I weight to specific sample design that we wanted. But technically, the way that the I weight is available in Stata, if you don't change anything in the programming behind Stata, you do the same way as the F weight, tab of a specific variable. Instead of F weight, you just use I weight, and then the name of the variable weight. And in this case, you can use fractional numbers. The A weight, it maintains the sample size. So the overall total from the table is going to be equal to the sample size. So if I want to do a table for my variable X, and I want to maintain for that example of Jose and Maria, the number 2 as the total, I use the A weight. And for regressions, we also know that we should maintain the sample size because we are not going to lie to the statistical software saying that we collected more information than what we already did. So we just do the regression. In this case, is a multiple regression, linear multiple regression, regress my dependent variable explained by these 2 independent, and then I inform A weight equals the weight variable. The only one comment, this information that I'm getting here specific about the weight, you can even look by yourself. You can just do help A weight or help F weight in Stata, and all this information here, I got it from the help menu in the help pages in Stata. One thing that's mentioned about the A weight is that it's more appropriate when we have databases like this, when we have averages for specific subgroups. So let's say that this one here is the average number of years of schooling for group 1, and average number of years of schooling for group 2. And we have 2 people in group 1 and 3 people in group 2. And let's say this is the average age for each one of these groups here. The thing is that actually the American Community Survey, the General Social Survey, and most of the surveys that we use, they are not organized as an average as this example here. It's more organized as a microdata, each individual in one row. So this individual here, in this example, has 3 years of schooling, 22 years. Another one, why do we have 2 here? Because we have 2 individuals. So the other one has actually 4 years of schooling, 30 years of age, and so on. In a way that the average between 3 and 4 is here, the average between 22 and 30 is here, and so on. So usually survey weight is collected from individuals and households, not as averages. So weights are not appropriate for most cases, but it also is widely used, the A weight, to analyze proportional distributions, both in tables and also to maintain the sample size in regressions. And finally, we have the P weight that it actually estimates variances, standard errors, and confidence intervals in a more precise procedure. It estimates what is called the robust standard errors. Because one of the assumptions of the linear regression is that the residuals, our error in our regression, are randomly distributed across all values of our independent variables. So we have this assumption of homoscedasticity. You have this homogeneous cloud that we're going to talk more about it on Thursday. But in most cases, our data is not, it doesn't provide, it doesn't conform with the assumption of homoscedasticity. So we have to estimate robust standard errors because our residuals are heteroscedastic. It's really hard for me to say these words. So the robust standard errors is pretty much a punishment that the statistical software is giving to you because you are not complying with the assumption from your linear regression, and they tend to be larger than the conventional ones. Not always, they are usually larger. And by the standard error being larger, remember the T formula. If we have a larger standard error here, a larger number here, will generate a smaller statistical significance, right? And that's pretty much a punishment that we are doing for not complying with the assumption of homoscedasticity. And the way that we do is similar to the A weight, the command regress, dependent variable, independent, P weight, and then we inform the weight variable. So this is pretty much a summary of how you use the weights in Stata. If you want to expand the population size and your variable weight is discrete, doesn't have decimal cases, you use the F weight. If it's a continuous variable with decimal cases, you use I weight. To maintain the sample size, you can also do tables, maintaining sample size with the A weight. And for statistical regressions, if you want to use the standard, estimate robust standard error, you use the P weight. But if you don't have a weight variable, but you still have problems of heteroscedasticity and you want to estimate robust standard error, you can just put a comma and write robust afterwards, even if you don't have a weight variable. When you estimate the regression with these two commands here, they don't estimate the adjusted R-square, the total sum of square, the explained sum of squares, and the residual sum of squares. If you want these specific statistics here, you do have to use the AE weight. Or you can run this regression and afterwards use another command called outreg2 that saves that regression results from Stata into Word or Excel. And we'll talk more about it on Thursday. But it gets a little bit more complicated when our surveys, they have a complex sample cluster design. In order to calculate the standard error, see, I'm not talking about means, I'm not talking about proportions, I'm not talking about the coefficients in regressions. I'm talking about standard errors. I'm talking about that measure that's going to give me the confidence interval. If I have a survey like the American Community Survey, and I just indicate the weight, and I don't inform the statistical software that actually ACS comes from a sample cluster design, Stata will assume that ACS comes from a random sample. So what does it mean? I would be saying that the Census Bureau had the list of all more than 300 million people in the US and gave the same chance for each one of them to answer the questionnaire in ACS. But that's not the truth. The truth is that the Census Bureau usually selects specific areas, sub-areas in the country, specific census tracts, and then go to those, after they select the census tracts, they go to the census tracts, get the list of all households, and then select the households and interview, get information from all people in those households. So we have different stages of selection, right? It's not a random sample that all 300 million individuals had the same chance of being selected in the sample. So we have to indicate to Stata the complex sample design of those surveys. And the main idea is that we have the mean, we have the proportions estimated correctly, but we need the complex survey design to correctly estimate the range of those means, the range of those proportions. In other words, I want to estimate correctly the confidence interval. And here I'm going to go a little bit faster. It's just, for each confidence interval, I can assign a different confidence level. Usually we use a confidence level of 95% when we estimate confidence intervals. And for this confidence level of 95%, the associated z-score is 1.96. And why am I telling you this? To kind of explain this formula here. So if I have a sample from my population, and I use the weight, and I estimated, let's say, the mean of income, this X bar here, and I use the weight. Let's say that I use the weight using the F weight or I weight or A weight. I used it, this mean is estimated correctly. But this margin of error is not estimated correctly. So here we have the sample estimate, plus minus the margin of error. And the margin of error is composed by the score of the confidence level. We saw that for the case of Z, the score of the confidence level of 95% is going to be 1.96. It's going to be 1.96 here. And we have the standard error. So this standard error here will be estimated incorrectly if we don't tell the statistical software that we have a complex survey design. The point estimate, that mean of income that I have here, is estimated correctly using simply the weight. But to estimate the standard error correctly and then the confidence interval, I need to inform also the complex survey design, right? And the same thing applies for regression, that same formula that we saw before. For the T-test, we also have the standard error being considered here. So it's going to be estimated correctly only if I inform the complex survey design, if that sample has a complex survey design. The point estimate of the coefficient is estimated correctly only with the weight. So let's show some examples. I showed you before in that microdata from ACS that we have a variable called PERWT, that's the weight for people, and the household weight for households, the HHWT. And if I just go to Stata and I try to see the distribution of the variable of the individual weight, I have some people that are representing only themselves. That's the smallest value that we find for that variable. And some people that are representing 2,313 individuals in total. So most of the cases, they represent few people, and some high cases, some few cases represent a lot of people. So those ones here. And for the household, I do the same summary statistics here, trying to see how it looks like, but I'm just careful to select just one person per household. So each household as well. Some of them represent only themselves, some of them represent more than 2,000 households, right? So this is just to show you how the weight variable looks like. So one example here now. If we do a frequency table for sex, tab of sex, using the 2018 ACS, I'm not using the weight. I maintain the sample size. I'm not considering the weights here. I'm just saying that I got information about 131,412 men and 136,688 women. But if I want to know how much they represent in my population, also these tables here are only for Texas. It's not for the whole US. I just ran only for Texas because otherwise it would take too long to generate it. If I use the F-weight variable to expand to the total size of the population in Texas in 2018, then I get 28.7 million, and I get 14.4 million women and 14.2 million men. And you see that the percentage distributions here, they are different, because here I took into account the weight. If I want to know how many households are owned or rented, and some of them don't have that information, this is the number of households that I passed through and collected information. If I try to expand to the whole size of the population of households, I have 10.3 million households in Texas in that specific year. You see that it expands to the population of households, to the number of households in Texas, and the percentage distribution also varies. So this is appropriate to do. This is appropriate to do, right? And even if I want just to do the percentage, I can do it from here. But I could get the same percentage using the A weight. So the ACS has a cluster design, and all this information here I got from the EPUM's website. The sample, whenever we have cluster design, we have to go back there to the documentation to learn which are the variables that were generated by the Census Bureau in this case to account for the cluster design. So the original variables that we used before will also be there. The weight, the individual weight, and the household weight. And there is also a household strata variable that we have to use to take into account the cluster design of ACS. These strata are defined as the public use microdata areas starting from 2005 and onward in the American Community Survey. So this strata is representing each one of these areas called PUMAs, the public use microdata areas, that are the smallest geographic areas that are available in public data. If you go to the restricted, if you analyze restricted data, for example, at the TXRDC, then you can go to the county level, in some cases to the group, to the block group level, and so on. But with public use data that you download from the EPUM's website, this strata variable is representing the PUMAs. And the PUMAs, they have at least 100,000 people in each one of those areas. And the idea of the Census Bureau is to group counties that are too small into these PUMAs, so we don't have issues of confidentiality. We cannot actually identify people with public data. And we have another variable that's available in ACS called cluster that identifies each household record in a given sample. So I have a cluster that tells me about the household, the strata, about the area, and then the individual weight. I have to use the three of them to indicate the complex sample design of ACS. And the command that you do this instead is called SVUI Set, the variable cluster, and then indicate P weight, the variable PERWT, comma, the option strata, and the name of the variable, by coincidence in this case, is also called strata. So strata, PERWT, and cluster are the variables that we have in ACS. And I run at the top of my command in Stata, the SVUI set. I'm pretty much informing Stata what's my complex survey design, which are the variables that I take into account. And then afterwards, if I want to estimate the mean of the variable y, or estimate a regression in which y is explained by x1 and x2, I simply write SVUI colon, and then automatically takes into account this information that I informed before, okay? So just one example. If I estimate the mean of income using the P weight, even with the P weight, they estimate the robust standard error, the mean is $31,175 in 2018, the mean income for people that have income different than missing. And the standard error was 39.98. If I multiply this number here by 1.96, as we saw before, and subtract here, I get this number. This number here multiplied by 1.96, and I add to this, I get this number. But wait, using the P weight, in this case, only the mean is correct, not the standard error, because the standard error is not taking into account the complex survey design. So let's say that I informed the complex survey design before, and then now I estimate the SVUI column mean income. See that the mean doesn't change. That point estimate, that specific statistic doesn't change. The standard error changes. And in this case, goes into that line of being bigger. And this number, bigger than this one, multiplied by 196, subtract here, this number is gonna be a little smaller than this one. 1.96 times this plus this number is gonna be a little bigger than this one. So here the confidence interval is a little wider, right? So we are less certain of where exactly our parameter is in relation to mean of income. So if I'm just interested on mean of income, this is enough. if I'm interested in the confidence interval, I do have to inform the complex survey design. And it goes further to say that if I want to estimate, let's say, the mean of a specific variable, let's say the same one, the mean of income, only for people between 15 and 64 years of age, I should inform that subpopulation within the SVUI command here, because then Stata takes into account even all other people that are not going to be counted here to estimate the mean of income, people who are below 15 years of age and people who are older than 64. It takes into account the full complex sample design of ACS. And for example, this case here, I just estimated what I had before, the mean of income. But in this case, when I did it this way, even people who did not report an income, have income equal to missing, they're affecting the standard error. So let's say that I want to know the mean of income. Of course, missing is not going to change the mean estimate. But when I do subpopulation, if income different than missing, my standard error is going to be different. And again, it's going to be higher, and it generates a wider confidence interval, right? Little wider, right? Here, just like 0.01 smaller than here, and here is pretty much the same thing. So just barely changed the standard error, but that would be the correct way to do it. And if you want to estimate the mean income for people only between 15 and 65, we have to say if age greater or equal to 15 and the age less or equal to 64. But in this case, again, I'm not considering that some people did not report the income variable. So to estimate it correctly, I have to do the subpopulation, consider only that group, and also reporting that I don't care about the missing cases. And it varies also a little bit, the standard error. But you see that always, if you used, the mean estimate doesn't change here. It's all about the standard error. It's all about the confidence interval. I'm not going to go in detail in GSS, but this, again, these slides, I did them all getting information from the General Social Survey website. And the weight variables in GSS, they have decimal cases, so they are continuous. So we cannot use the F weight. But even if you use the I weight trying to expand the population size, they will not expand because some of the weights are below 1 unit and some of the weights are above 1 unit. And here's just an explanation about these 3 different weights that we have in GSS, but we pretty much just use this one here, the Ttest all, which you can apply for all years of the General Social Survey, even before 2004. And you can do a table for any one of the variables or summary statistics of your variable. And since it's not expand to the size of the population, I weight gives the same result as A weight in this case. So I usually just use A weight with the General Social Survey, right? And General Social Survey also has a cluster sample. You first select specific areas, and within those areas, you list sub-areas, select specific sub-areas, and then you list households, and then you select the households. So we have 3-stage units in GSS. And the variables that you have to take into account are the variance stratum called V-strat, and the variance primary sample unit, the VPSU. So these 2 variables are available in the General Social Survey as well as the WTS all. And the SVUI set that you use for General Social Survey is this one here. The weight is informed here. The strata is informed here. The primary sample unit is informed here. And if I have just one unit for each one of my areas, it scales to the average of that specific sub-area. These SVUI set commands, if I'm using a survey, I do not know exactly how to use them for that specific survey if I don't read the documentation. This command here, it is given to us by GSS. That previous command about the complex survey design for ACS is given by the EPUM's website. So the SVUI set is not something that I come up with out of my head. I follow the instructions of the complex input design available in the code book, in the documentation of that specific sample, of that specific survey. And in the same way as we did in ACS, after we inform the complex survey design, you can estimate the mean of a specific variable or regression of y by x1 and x2, just inform an SVUI column before that, right? This is just a technical thing, and we'll pass it through. And here, from now on, it's just like I can go really quick here, so you can ask questions after these examples, or now if you want already. Someone asked a question there. Wow. Oh, Mark is writing a lot. I didn't see that. So I will show here some descriptive statistics for nominal level variables, ordinal level variables, and interval ratio level variables using the 2018 ACS. So in this case, I have here, we use in the 2018 ACS, we have the variable race and the variable ethnicity, Hispanic or not. And then I just created a new variable, race F that I created this new variable that's going to tell me if the person is white, no Hispanic white, no Hispanic African American, Hispanic, no Hispanic Asian, no Hispanic Native Americans, and no Hispanic other races. And using their weight, I know that based on ACS, we had 327 million people in the US, living in the US in 2018. And taking into account the weight, this is the percentage distribution of that specific group. What's the sample size of these people here? One other command that I can do instead is just count if that specific variable is different than missing. So these 3.2 million people here, they refer to 327 million people, right? So we expand it by 100 times. And if I do a table like this, this is how I report a table about race ethnicity distribution in ACS in a paper. No, I have to organize it. And that's something that Mark will emphasize more in the last session of this workshop series. So I have to organize this. Usually, if it's a table so small like this, I can manually organize it in Excel or Stata. And then I put the title. I number the table. I explain what exactly are my subcategories. Numbers aligned to the right. The total percentage here. I have the population size, the 327, that comes from here. The percentages comes from here. And the sample size is here. So the population size and the sample size. The source of information. And tables don't have borders on the left and on the right when you have numbers, right? It's just on top and bottom, some in the middle you can have as well. So that's an example of how you report a table in a paper, in a class paper, or in a paper that you're trying to publish and so on. In a conference paper, for example. This is an example of a graph bar for race ethnicity, also in 2018, in percentage terms. And just to show that the graph bar also uses the weight. And this is the command in Stata. So I'm doing a graph, a bar graph, using the F weight, exponential the overall size of the population by the individual weight. by the variable race, and this label angle here is just the angle of my label, and the Y title, I put it %. So this is important. Whenever I do graphs in Stata, if I try to do them fast, if I had this table here, I want to do a graph really fast, probably I would just copy and paste this table in Excel and do it. Graphs in Stata, if you want to format them correct, you have to write a lot of sub options here after the comma. And I learned a lot about how to use the exactly options there by Googling it, by looking at the help in Stata, right? Because these graph comments can get really, really long. A pie graph for race ethnicity, just to show the same variable using different kinds of graphs. Over race, and they all explode like this. And you are showing all categories, right? Education group, this variable education group, I also created it in Stata. So people with less than high school using the F weight. So we have 327 million and 97.7 million less the high school. That's almost 30% of the population, and the same sample that we had before. And organize the table to put it in a class paper, in a conference presentation, or in a paper that you wanted to submit for a journal. Always being really clear with everything that you're putting out there, right? So all this information here, I got it from these two comments, this one and this one, because they also included the sample size. This is a comment that I want to know some statistics about income. So in this case, I have only 2018, but this comment table is different than the tab. The tab is a short for tabulate. Table, I put table, a specific subgroup that I want to analyze, the weight, and I want to have only information for people that have income different than 0. And the contents of my table will be the minimum value of income is here, the 25th percentile of income, the 50th percentile of income, which is my median, the 75th percentile of income, and the maximum income. This comment table allows us to put only 5 statistics there. So that's why I ran it again afterwards to get the interquartile ratio here of income, the standard deviation of income, and the mean of income. And I also calculated the sample size. These 3 different comments are organized, and also, since I want to know the correct standard error, this standard error here, or the standard deviation of income, does not take into account the complex survey design, only the weight. In order to calculate the correct standard deviation of income, I use the complex survey design. I'm doing for that specific subpopulation with valid information of income, different than 0. The mean here is pretty much the same as we saw here, 50,043.98, the same thing here, and the same thing here. But in this case, with the complex survey design, the standard error is being estimated correctly. And based on this standard error, I get this standard deviation for income, 61,547, which is different than this one here. So the standard deviation, I do have to take into account the complex survey design. And then I organize these 2 slides into this table. The mean, minimum, until the maximum, the range, the interquartile range, standard deviation, population size, sample size, and some cases. Okay. A histogram of income, also showing a normal distribution there. This is similar as before, but in this case, I'm doing the same table, but now by a variable that varies, in this case, sex. So I get the mean income and median income for men and women, and by race, ethnicity, by years of schooling. I can do also graphs in Stata mean of income by age for each one of the single ages, mean of income by each one of the single ages and by sex, and all that using the weights, right? And I can also do box plots in a really straightforward way in Excel, in Stata. Where's my mouse here? So I'm doing a horizontal box plot of income different than zero, and using the weight, I get this information here. I can break it by sex, just by doing here over female. I can break it by race, ethnicity. I can break it by education group as well. Okay. And like I said, you can do really nice graphs in Stata, but they can get really long. This one, I really learned it by Googling it, how to do age sex structure in Stata. And this is the command to do it. But before that, I had to generate a series of different variables here. And it generates the age structure for the US as a whole, for Texas. It's really large file, so it goes slow. So in Texas, and then for Brazos County, right? Really young population here in Brazos County because of the university. And yeah, so that's what I had to tell you guys. And just to show you in our website for this workshop, under here, additional material or introduction to social statistics using Stata. If you click here, again, you go to that workshop that I did spring last year. And here you have this data code. If you click here, you have this, I guess the number 2, right? The simple weights, this one here. You have all these data codes that I used to do the graphs and tables that I just showed in my presentation. They're all here. Everything is here until the end with the box plot and the age sex structure. Yeah, age sex structure is here. You can also download the ACS 2018 from here. That's a zip file. And I also put it available here. So if you download this, you will be pretty much getting this. It's going to be a zip file called course.zip. If you unzip it, you're going to have this data folder with data for 2018 Brazos and Texas. I just put Brazos and Texas to be smaller and easier for you to do some analysis. Some documentations. See, I had to go out there to see how to use the weights in GSS and ACS. I put GSS here as well, just for you to see how I collected that information. And the programs 1, 2, 3, 4, 5 relate to that workshop in my website, right? So this one's here. 1, 2, 3, 4, 5. And this stata2.do that you can open in Stata, if you open in Stata, it's going to look like this. It's exactly all the file, all the commands that I ran to generate this lecture. Okay. Thank you. Any comments? Yeah, I think you, Mark, had a lot of comments there, right? Also, the C becomes stat in the new table comment instead.
So I'll add that your practice of putting the details of the graph command into a program is really important, because if you do the point and click approach, which is very tempting, it'll be really hard to reproduce the graph exactly as you want it each time you come back to the analysis. And then, so one of the tricks you can do is you can you can work with the point and click menus to find some of the esoteric options and experiment with them. And then when you get it tailored the way you like it, just cut and paste the syntax of the command as it is in your log output. And then you can put it in your program and get exactly what you want. And then the next time you don't have to remember all that crap.
That's right. Yeah, I always go back to my own codes.
Yeah, you know, if you get one really good design on a graph as an example, you can just cut and paste that sucker across all kinds of programs and make little modifications. And why reinvent the wheel every time? You know, just.
There are comments here about the cluster design. I will copy them and add them as to new slides. They are good.
Yeah, well, it's I remember in graduate school, Ernesto, did you know Norval Glenn?
No.
Yeah, well, he was still teaching when I was in graduate school back with the dinosaurs, and you know, he published extensively using the General Social Survey, and was an expert on the consulting panel for NORC for the GSS design, and he publishing work using the GSS. He said basically your standard errors, because of the cluster design, the true standard errors are about twice what, 1.5 times the size of what they would be if you don't use the proper weights. You know, if you just treat it as a simple random sample, the standard errors are a lot smaller than they should be, and you get findings. And so whatever you wanted, you did not want Norval Glenn to be the reviewer on your paper because he would make you do it the right way. You'd hope to get a lucky draw on a reviewer who didn't know this.
And that's true. I mean, it depends on the reviewer, right? Who's in the committee and so on.
So that was a joke. Of course, we all want to do it the right way, no matter how much extra work it is, because we're scientists and we have lab coats.
That's cool. Yeah, and in the complex server design, like I said, you learn how to set up the SVUI set, which one is developed by really going into the links of the specific database that you're analyzing. Like with ACS, the public available data is in epums.org. And then under the slides that I copied from them, I put the links there. And for the General Social Survey, they also have a really nice website. And both of them, I don't even create a code book whenever I use them, because their website is really easy to find the variables, and it also has information such those technical details about the complex server design as well.
So one thing that I've observed is that concern about survey weights varies by kind of sub area. So demographers pay a lot of attention, and in part that's because descriptive statistics, which a lot of demographic research involves, they can be very dramatically affected by the survey design. And if you have an oversample of, let's say, areas with poverty populations, and you don't use the right weights, you'd make your population would wind up looking poorer than it really is. But a lot of surveys would want to oversample a poverty area because it would serve the needs of their research objective. And then in the health area, so back when Verna Keith was in our department, she made me aware that in health research, where a lot of the data sets are extremely expensive, so they're very well crafted with complex survey weights, if you don't use survey weights, they won't even review your paper. And they often actually specify that you use a particular piece of software called Sudan because it has the ability to handle some extra complicated survey designs. And so know your field, and if people in that area expect you to use the survey weight procedures, then whether you like it or not, you're going to have to do that.
And the example of like some samples over representing specific subgroups is important, because in that case, if you want to analyze just that specific subgroup, maybe the weights is not so important because you're not comparing them as much with the overall population. You're just trying to do kind of like an in-depth analysis of that subgroup if you have an overpopulation. But then if you want to talk about the whole population, not just that subgroup, then you would need to use the sample weight and the complex survey design if it's available.
Yeah, that's a really good point. That it's much more important for descriptive statistics than especially if you use a stratified design so you can compare groups. The survey weights would be important for getting descriptive statistics correct, but maybe not so important for getting the group contrast, as long as each group is representative of its particular group.
Dr. Amaral and Dr. Fawcett, so would it be safe to say that you want to expand your sample when you are trying to generate tables, and you want to maintain it when you're doing regressions?
That's usually the case, but for general social survey, you saw on the descriptives of the weight variables in ACS, American Community Survey, the lowest weight was 1. For the general social survey, some people represent less than 1. So the weights are constructed in a way that even if you try to expand the population size, it's not going to do it. It's going to just expand to the sample size. So the general social survey, the main idea of that survey, it's not to generate absolute numbers in order to understand counts of people. It's more to understand the proportions, the distribution of people in different subgroups. So in that case, even if you want it, you are not going to be able to do it. In another paper that I did with Dr. Sakamoto using the current population survey, CPS, the CPS, like the weights is pretty similar to the American Community Survey, but we were talking about a really specific subgroup, second generation immigrants from Nigeria. So Nigerian Americans born in the US, parents born outside. So our sample size was really, really small. So any table that we showed, we did not really want to say how many Nigerian Americans were in the US. We just wanted to show the overall characteristics, right? By income and education, for example. So in that case, just made sense to use the A weight to maintain the sample size. Although we could use I weight or F weight to expand the population size. But the subgroup was so small, we were cutting so much CPS, and CPS doesn't have a large sample size as ACS, that it was so small that by saying that would be the number, the absolute number of Nigerian Americans in the US would be wrong. So it depends a little bit on your research topic in the group that you analyze. That's why that I also show in these slides that you can also do the tables maintaining the sample size. For example, for that case, we have in a really specific small subgroup of the population.
It also depends on the audience that you're trying to reach and the goals of your presentation. So a lot of the demographic data sets, the readers might want to know a national population estimate. So you would use the weights to produce those numbers in your table. And if everything's been weighted properly to begin with, none of the proportions will change, just the numbers. And for an audience that wants to see just the proportions, and they may want to know what the actual sample size is, and that's underlying those proportions, you might not use the weights to generate population counts. You would use them to show the sample size underneath the proportions and means that are being reported in the table. So it would give away that you only had 3 people to estimate those 5 million.
Yeah, so that's my point, because like in this example of the second generation Nigerian Americans, we got data from, I think, 2009 to 2019 CPS for all these years, like 10 years of data. And we got around 150 Nigerians with valid information of income. It's 10 years. And if we would use the way to expand the population size, I don't think that would be completely inappropriate. But still, we can look at the sample size and their distribution by income and education, which was the focus of that paper. And once I asked the question there. So you don't have the weights available in your data set, right? You're asking if you can generate the weight?
Yeah, there's no weights because it's just administrative data from the school district. And so I've been trying to think about how do I account for D and S, right? Like within a given school, when there are very few schools that are integrated across race.
And I think, Mark, you'd be better to answer that, but I think it would be good to leave it as it is, right? Since it's administrative data.
Yeah, it sounds like full count data, which is good, because segregation index scores are very sensitive to moving to sample data. The assumption behind most formulas is that you have full count data, so your administrative data meets that requirement. That's good. And then I think it becomes a question of the index score that you're computing and how you want to interpret it. So if you compute an index score within a school, that has a meaning in that context. And then there would be a score that you might compute for all schools combined, and that would have a different interpretation, a different meaning. And then if you are you trying to do any decomposition analysis?
Yes, that's what I'm trying to do.
Because well then there will be formulas where the overall index score can be decomposed into the segregation that occurs across schools and the segregation that occurs within schools. And then you'll need the full set of scores. And then there's a series of what they do get aggregated through a series of complex weights, which is the weights there are a little bit different. They're not survey weights, as Ernesto was discussing. They're weights that are dictated by the nature of the index formula. And so that, I would call that not easy, not simple. And
I say I'm not convinced I'm going to get that.
Yeah, a few years ago, I had some students who were interested in that, and so I worked up some very detailed examples, and we sat down as a group for an afternoon and figured out all the dang weights. And I'd be willing to resurrect some of that, but it's a different use of weights than than the use of weights with survey data.
Yeah. Okay. So you don't, in terms of, okay, well, so if I am trying to do a decomposition, then I do need to use these not easy weights. But if I'm trying to just estimate like what predicts S at a given school, given that I do have full count data, do I understand correctly that I don't have to worry about, you know, the number of Latinx students at that school?
You don't have to worry about it. You don't have to worry about it as a weight option.
Okay.
You only have to worry about it if it might be relevant as an independent variable. So it would be a non-statistical concern. It would be a substantive concern.
Okay.
But maybe somehow ethnic composition of the school has an impact on the level of segregation that occurs in the school.
Mm.
So that's switching from a statistical issue to a substantive issue. Does demography matter for social interaction and dynamics? The one thing that I would say that if you have different schools as your units,
Mm-hmm.
some schools may have very large enrollments and others may have small enrollments.
Yeah.
And because of that, you'll get heteroscedasticity in the residuals from your regression analysis. There'll be larger errors of prediction on average for the small schools. They're more subject to random influences just modifying the segregation score.
Yeah.
So that's a pretty common pattern, that whenever your units are aggregations, subgroups or cities or counties, the smaller ones will have more volatile outcomes. It could be the same underlying social process, so no true difference in the underlying social dynamic, but because it's a small community or a small organization, random factors can move it away from the true average more easily than would be the case in a large aggregate.
Yeah.
And in that case, even if she doesn't have the weight, but she has the information for example, individuals and then the school where they are, she can estimate the analysis, even regressions, with the cluster option by saying that pretty much you're saying that people that are from the same school, they tend to be more similar to each other than people from other schools. So that would be an option within your regression, with after the comma, cluster, and then the variable with the school identification number.
Okay. So if I was doing within school, then I guess the cluster would be classroom.
Yeah, that's right. Because I was thinking more like individuals in different schools, but if you have just one school in different classrooms, then theoretically it's reasonable to think that people from the same classroom tend to be more similar to each other, then it would be reasonable to do the cluster.
Okay.
I would say so. Yeah.
All right, thank you.
So I'm going to put in a plug for people to brainstorm. If a session like this is useful, well, that's neat. But there may be sessions that we do where, that's nice, but it's not really something that speaks to the issues that you're going to be concerned about in your own work because of the subjects that you're working on. So let us know what kinds of things you're working on and the kinds of questions that come up. And so I'll give you some examples. There's a lot of jargon in statistics, and like fixed effects and difference in differences and so forth. We could have a session where we just try to sort those terms out. It's like people in economics and sociology are separated by a common language that they do not have. They use the same term, they use different terms to talk about exactly the same things.
Elasticity. I mean, it's just Why?
And so, that would be kind of fun, just to make a list of all these terms and then try to sort them out. Another one, like this summer, we just picked 6 topics that were feasible, and there was some interest. And like a lot of people have questions about what to do with missing data. You could have a whole course on that, but maybe a session during the regular academic year would be useful. At least, point a few things out to where you could go for readings and things. So please use your imagination and give us some feedback. Peggy and Luz may be following up, asking what your thoughts are and anything you'd like to suggest for topics in the regular academic year if we continue this.
Yeah, and like Mark said at the beginning, maybe those monthly method sessions that we would have throughout the semester could cover exactly those topics that you guys would like us to discuss. And just to highlight, if you are having problems just running those stated comments that I uploaded there, that just for you to train a little bit and test it, you can either contact me or Peggy, and then we can help you with like running the comments. Okay.
So here's a really esoteric tip. If you are running a program in Stata 17, and the program worked with Stata 16, but it doesn't work in Stata 17, I think you can give a command that will revert. If you issue it's an esoteric set command, and it will revert back to the syntax from an earlier version.
It's like version Stata 16.
Maybe you've got a big program and you don't want to go back and edit every single line and make it work. So that's an option to consider. Or another one would be, don't uninstall Stata 16.
Yeah, I have to redo that. Yeah, for 17. Yes, thank you. Yeah, thanks for the comments. And we'll be back here on Thursday at 1 discussing linear regression. Okay.
Thanks again.
Great.
Thank you, everybody.
Thank you.
Mm-hmm.